hi, I'm John David Dalton. I was formerly the performance program manager at Chakra. I'm also a JavaScript library author. I develop Lodash. Right now, I am in the the web frameworks ecosystem team under MS Edge, so you'll be seeing me do a lot more open source work, doing pull requests on your various projects and things like that. But today's talk is on built-ins written in JavaScript. So let's get into it. So I titled the talk Drawing Hands because it's JavaScript built-ins written in the language itself, under the hood. So you can't observe that it's written in JavaScript, but it actually is. And so this allows you to power it. And so this drawing here was, the lithogram graph was done by MC Escher. And self-hosting, I'll be saying this a lot, this is when parts or whole of a language is written in the language itself. But what is this? Ray? This says Bango on this. Baby wipes. Did you leave this here from your first talk? What? Here. Krill says hey, by the way. Yeah. All right, now that that's done. That was my most important bit. All right? All right, so yeah, you must be here for this. All right, so first I'm going to go into the good, the bad, and the ugly of built-ins written in JavaScript. So first, let's talk about the good things. So ease of development. Because they are built-ins and they're written in JavaScript and these engines are open source, you can view them, you can see them, you can examine their code. We're going to look at their code in just a little bit and kind of see how they're made. So it allows you to contribute back to the project. See, more contributions, naturally. Performance. The good thing is it's widely used to allow the built-ins to leverage the same optimizations that your normal JavaScript gets to leverage from the JIT. So you get inlining for free. You don't have to do any extra work there. And so there gives you some superior performance. So some engines like Firefox and Chrome, browsers like Firefox and Chrome, will use JavaScript to implement array for each, filter, map, every, and all of those because they get the inlining benefits. So experimental API. So this is something I'll be digging into a little bit later in my job too, is anytime there is an experimental API like a proposed API from the W3C, you can use JavaScript to implement that quickly and get that into an experimental build and testable. And so devs can try it out and use it. So examples. What do I mean when I say examples are JavaScript methods built in the language? Let's see. Do I have any examples here? No, I don't. But I can go over here, and I've got them. So here's an example of a built-in written for Mozilla SpiderMonkey. And this is, I'll zoom in here and zoom around so y'all can see a little bit better. Here we go. So here's array index of. Array index of is pretty straightforward. It's basically, you give it, so you have an array and you're looking for a needle in a haystack. You're looking for the index of a given element. And it does strict equality comparisons. And so this, if you're familiar with shims, this looks really close to a shim, right? And you can see down here, it's doing a little extra check though. It says, hey, if this array is packed, so there's a concept in arrays, and the older ES5, ES3 methods had to be aware of this, is sparse arrays. Sparse arrays are these things that I don't deal with. I treat them as all dense, but they have performance impacts. And so that's why this JavaScript function is forking its behavior based on that. So this is calling into a helper that is, I believe, C++ code that allows them to detect if an array is packed or not. So basically dense or sparse. And then it goes here. So now we've seen that. That looks pretty straightforward. Let's look at, let's see. We don't need to see the is packed. This is the check right here to see if a value is packed. And I'm not a C++ dev, so I really don't know a ton of what's going on there. But you can see that you can mix JavaScript and native methods together to create your built-in implementation. And that's really cool. Here is V8's version of index of. So we can zoom in here. You can see it's doing the same kind of juggling. It's doing length checks. It's doing the same use, like the use sparse variant check. And there it's having to make an inference about the array. So it's having to guess if the array is likely to be sparse, and then go down this path, else go down another path. So you notice that here, they may not have as much insight into the engine or into what's going on with the values that's being passed because it's just JavaScript, right? So that may be an issue with implementing it in JavaScript. Now you can see here the Lodash implementation of this method. And what I'm doing here is detecting if a value, I do a little bit of argument juggling here. I detect if you're passing true to be able to do a binary search, or if you're passing just an index to do something like a from index. And from there, I also match, I throw more functionality into this, and I'll get into this in a little bit with features. But with JavaScript implementations of your built-ins, and if you're leveraging JavaScript, I've found a way in Lodash to have better than built-in performance implementing a simpler subset of the built-in functionality. But what I'm able to do on top of that then is go back and add features and still be on par or better than built-ins. So in this case, I'm also doing a check for NAN. So normally index of doesn't support NAN. If you try to look for NAN, it's always going to return -1. But in this case, I've added support for that because ES6 is starting to be able to match NAN values, like if you have a set or a map. So I wanted that to be consistent throughout. So you can see here, real basic implementation. Did you see the previous implementations were very complex. They had all those forking for different cases and conditions. But you can see here the vanilla JavaScript version is basically a for loop doing the strict equality check. And you notice that if it's NAN, I hand off to another helper function because that's not the common case. So these kinds of principles can also be applied to your array built-ins in the browser. So we'll look at that. The next example I want to show and discuss is INTL. So the Internationalization API, and that's this spec here that I'll zoom in on because everyone likes reading technical specifications, talks about the INTL object. So in IE and in MS Edge, we implement the INTL Internationalization API in JavaScript. And so there's pros and cons to that. So we got in on the self-hosting game as well. So let's go back to here. All right. So the good here. The good was we were able to write it in JavaScript. It was able to simplify the arguments, handling of the arguments. It was able to be understood and read. So like I'm not a C++ dev, but I know JavaScript. So I could look at that and help out and say like, hey, this or that. Other people, JavaScript devs that we have, could do that at the company. So it was good. Simplified reading and understanding. Integrating with C++ was simpler than we thought, so that allowed us to spin this up rapidly and get that implemented. But with the good comes the bad. All of that JavaScript, you can coerce values, you've got value of, you've got prototypical inheritance. All these ways that you can manipulate the language to cause side effects. And your built-ins shouldn't have side effects, right? They should just be isolated. You shouldn't be able to mess with the surrounding language and affect their behavior. So all of that had to be guarded against. And so that was tricky to do. You have to create and hold references to normally functions you take for granted. And you have to find ways to guard against people changing things on the object.prototype or other methods that would cause your functionality to have side effects. There's also heavier boilerplate. Because of all of that, spinning up the development of that single implementation took longer. It took more boilerplate to get that ready. Now, hopefully, future implementations will already have that boilerplate in place. And then the ugly. So I already mentioned preventing tainting of internal JS objects, but then you have to be able to test that and try to ensure that you're guarding against that. So it not only complicates the guards, so the implementing all the guards around it, but also the testing of those too. And then also ensuring that you have the correct stack behavior. So if you're debugging and you want to walk the stack, you don't want to go into the internals of the built-in. You want that to be obscured and hidden away. I remember there was versions of V8 that had their built-ins written in JavaScript, and you could toString them and view their source. And I was trying to find the version of that, because I always thought that was so cool. But apparently, it leaks things that aren't supposed to be leaked. But awesome. And this would be another one, too. You don't want to walk your stack and then dig into the internals of the built-in. So there's that. The bad and the ugly, now moving on to other things. Before I said, hey, it's great for performance. You get inlining. But you also, and I hinted at this earlier, you also don't have all of the tools and optimizations and data available that the engine would behind the scenes. So that's why the V8 implementation was having to make a guess if something was a sparse array, right? They didn't know right out the gate that something was. And so that can cause overhead. And so I'll show you this. Going back. In 2012, I had a conference talk. And it was called The Hidden Cost of JavaScript Natives. And that's where I went through and showed every built-in and how they were horribly slow compared to vanilla JavaScript alternatives. So that was in 2012. And one of those links was for, let's see, index of. And I showed the performance of native versus the vanilla. So let me go to, let's see, this one. And let's see where we're at. Live demo. Oh, yeah. And we're moving on from this. The benchmark would show that we're still behind. So even with implementing these methods in JavaScript, they're still not as fast as simplified alternatives. So performance isn't guaranteed. Oh, sorry. Well, this slide here isn't really important. I'll go back to the other one. Cool. So no silver bullet on performance. But I've noticed that in those cases where you come out of the gate without the performance, here's one. Object.assign. I was very psyched as a library author to use this method. And as soon as it appeared in Windows 10, I tried it out, and yay, we were 60% faster than vanilla JavaScript alternatives. So I was going to use it in Lodash. But then I looked at the other browsers. And Firefox Nightly, hey, they removed their try-catch logic. And Object.assign is on par with JavaScript alternatives. OK, so it's on par or better. That's great. But V8, it's 62% slower than JavaScript alternatives. So it puts me in a tricky spot of having to make tough choices about whether I want to go through all the hoops to fork my code to use this built-in when it's not as performant, especially in a scenario that's like a node-specific scenario. So the lesson there is that these methods are all written in JavaScript, and they're self-hosted, except for chakras. And chakras was the one that was the fastest. So in that case, we took the lump for implementation, ease of implementation. Yes, it was harder to implement, right, than, let's say, writing JavaScript. But the end result was a faster method out of the box. And we still have room to optimize. Like this was, normally when you create these methods, it's implement first, get all your unit tests passing, push it out, and then go back and optimize, right? So this is our right out of the gate performance. And so if we want, we can go back and iterate over that and improve that. But right now, we're already giving developers what they want, which is an API that's fast enough that they don't have to sit there and pull in another library dependency. which brings me to developers shouldn't be forced to use a library to have faster built-in equivalents. I shouldn't have to write Lodash to have faster built-in performance for these common utility libraries. So I've been pushing at Chakra to optimize our built-ins, and so that's what we've done. We came out with a blog post where we talked about specifically array index of. That wasn't a random method picked. They crawled the top sites, found the most used JavaScript methods, and then put them on a priority list for optimization. And array index of was one of the highest ES5 methods used. So I would say expect more of that. I want to challenge the other browsers too to get involved in this and optimize your built-ins because we're creating a situation where we spend so much time creating these methods, specifying these methods, testing these methods, implementing these methods in the browser, and then having such poor performance that developers aren't using them. So who are we making them for, right? We should be delighting developers with things like optimizing the built-ins and optimizing the usage paths from ES5 to ES6. So for example, your spread operator should be fast, and the alternative to that should also be optimized. So you're not getting a penalty for switching to a new syntax. They should make sure that the fast paths from one translate to the other. And so that's what you'll start seeing a focus on, is more built-in performance. I'm going to hit the next slide, and I don't know where it's going to take me. So here we go. All right. Whew. Optimizing the built-ins, which I've already talked about. Nice. One more. All right, that's the end one. So I knew it was close. If you want to talk to me in the hallway, I'll talk to you about the other issues and tweaks with this other work we're doing with optimizing our built-ins. And that's it. Cool. Thank you.